Okay, yeah, so it should be recording now, and welcome to the 8th recitation. And yeah, I guess we'll get started. So today we'll be going over assembly and then just PA4, and I'll give you a little GDB demo on the BOM that you guys have to diffuse and how to use GDB to diffuse it, because that's the main tool that you're gonna have to use. And yeah, so the third programming assignment is due Wednesday, 11:59 p.m., which is tomorrow, and BOM Lab is out. So make sure to get started on that. So I guess let's just get started with assembly then. And okay, so we went over this last time, which kind of operators you have offered in assembly. So you could basically perform operations on register or memory data, and you could transfer data between your main memory and the register. And then you have the assembly equivalents of your if statements, while loops, for loops, go-tos. And then we have, okay, yeah, so we went over what registers were, and they're basically these places in the CPU where you could store things temporarily, and the CPU can access them very quickly. So yeah, so we went over this too, and we went over how in the version of assembly that we're going to be working with, which is x86-64, we have 64-bit or 8-byte registers, and all the other registers other than RSP and RBP are general purpose. And you can also access the tinier portions of the register if you need to. So if you just want to use these first 4 bytes here in RAX, you could just refer to EAX. And this comes from the 32-bit registers that we used to have before. And we still do in many computers today. So yeah, so in EAX, there's further decomposition where you could also access AX, which is half of that, so the 2 bytes. And then you could access individual bytes even if you wanted to, which would be accessed using these codes. And yeah, so this is kind of where these names originated from, such as the name for EBP, which is base pointer, and ESP, which is stack pointer, and source index, destination index, all of this stuff. But yeah, so that's just some history of where the names came from. And yeah, we also went over this, moving data between registers and memory, and just placing like numbers or an immediate value, which would just be a constant into a register. So yeah, so we went over this too. So if you wanted to move the number 123 into the register RAX, we would just do call move Q, and the first parameter is the source, which would be the 123 with the $sign indicating that it's an immediate value, and then the destination, which is the register RAX, and the percent sign indicates that we're talking about a register here. And yeah, so we went over this stuff, and these are just different move operations that we have. So basically, this slide just shows you how you can move things between memory and registers and stuff like that, and what the C analog of that would be. So if you wanted to move the value 0x4 into the register RAX, that could kind of be analogous to temp equals 0x4, where temp would be the register RAX, and now it holds the immediate value of 0x4. And yeah, so all of these, you could see that it's like a pretty clear correspondence of how it relates to the C analog. So the variables just represent registers. So if we wanted to move RAX to RDX, we just set temp2 equal to temp1, where temp2 represents RDX, temp1 represents RAX. And here, so yeah, something you need to know is that the parentheses in assembly or in x80, yeah, in x86-64 represent dereferencing sort of. So like that's the best way to put it. So here what we're doing is moving RAX into what RDX contains. So we take RDX, dereference it, and then take RAX and move it into that. And that's exactly what's happening here. So you take P, which represents RDX, you you take P, you dereference it, and then you set it equal to temp, which was our RAX. And yeah, so that's basically how you move things around from immediates to registers or memory in between registers, and from one memory location to another. And yeah, so then we have this basically just talks about pointer dereferencing, which is what we just talked about. The parentheses represent pointer dereferencing, and if you have an instruction like this, hello, okay, yeah, you could just cut me off if you have a question or something, but if you have a an instruction like this, and you have 8 with the RBP in parentheses, that means we want to access RBP plus 8. So we take whatever is that RBP, add 8 to it, and then dereference that, and then and that's the value that we're talking about here, and putting it into RDX. So that's what this 8 here does not mean multiplication. It mean that's just how we signify that we want to add 8 to the register. And that's what this is talking about here. So if you take a register R and you have a displacement D next to it, then what you're doing by writing it like that is accessing memory at the register R, whatever is at register R, plus an offset or displacement of D. And yeah, so from there, we can just talk about this function that we have here. It's called swap. And so it'll take 2 parameters. It'll take a pointer to a value of type long and call that xp, and then another pointer to a value of type long called yp. And this is a pretty simple swapping algorithm here. So we just take t0, and t0 contains whatever's in xp. So we take the pointer, dereference it, and set that value to t0. Then we take yp and dereference that and set that value to t1. And then we just replace them. So in xp, instead of in xp, we just set it equal to t1, which was the value in yp. And then in yp, we set it equal to the value in t0, which was the value in xp. And so that's basically how this function works. And then we have a very similar function here in assembly. And this slide clarifies exactly what it's doing. So basically, well, first we want to take a look at this this box here that that basically maps the registers to the variables, so we can follow along. So here RDI has the value XP, RSI is YP. So these are the parameters. and RAX is T0 and RDX is T1. So basically what we're doing is first we dereference XP or RDI in this case, and we put that value in RAX, which is T0. Then we dereference RSI and put that value into RDX, which is T1. And so that's equivalent to these two lines. And then we move the value in RDX, which now contains the value of YP into the memory address at RDI. And then we take the value in RAX and move that into the memory address in RSI, where RDI and RSI were XP and YP, but we put the switched values into them. So we set XP equal to T1, YP equal to T0, and then we just return, and that effectively switches out of it, or that effectively swaps the two values. And what you see here, this is a label for these instructions right here. So in assembly, basically a few slides ago, it'll take way too long to go back there, but a few slides ago I said that you have what's equivalent to a go-to sort of in another language. So in like in actual language, you could say go to this function or something like that, or go to this line number, and if some sort of condition is met. So here we could possibly in assembly compare two values and then tell it to execute this function swap. And then so that would go to the label that says swap and execute the lines that are associated with that. And then we have, so before what we talked about was simple memory addressing, but now we have complete memory addressing, and this is a little bit more complicated, but it's not so bad. So basically before we just had one register here and then the displacement next to it, but now we have the displacement, and then in parentheses we have three things. So we have the base register, and then we have the index register, and the last thing is the scale. So basically, let's take a look at what this means. So if you have something like does anyone have any questions? Yeah, so basically if we have an instruction like this, or like this piece of code in an instruction, then what this does is, okay, so it's saying that we want to multiply the value in here by 4, and then we want to add EBP to that, and then we want to add 8 to that. So that's what this is telling you. So what we're doing here is taking the value at register RI, multiplying that by a scale of S, and then so this becomes one value, and then to that we add our RB or whatever's in RB, and then we also add the displacement after that. So this is a complete way of writing what you want to access from memory, and so this allows you a lot of flexibility in being able to multiply and by a scale or add a displacement to get to just a specific location in memory that you want to get to. And so that's what this can be useful for. So it's basically just this formula that corresponds to an instruction like this. And then we have, yeah, so if it's only, if it's two registers like this in parentheses, that means you just add, you take whatever's that register RB plus register RI and access memory at that location. And if you have a displacement next to that, you just you do the same thing, except you also add the displacement and then access the memory at that location. And then in the third case, instead of the displacement, it just has the scale. So we basically just do what we did here, multiply by the scale, add that, and then access the memory at that location. And here's a little example of what this does if you try to, okay, so let's say you have a character array called A, and it's of size 10, and we want to access A at index 2, then this is your array, and A points to, as we know, the first or the zeroth index, and so let's say RBX points to or RBX contains A, right? So to get to the second location, we want to take A and add 2 to that, so we could access whatever's at A at index 2. So to add 2, we just multiply RBX by 2, and that'll get us whatever is at A at 2. And so that's basically how memory addressing works. And so the assembly instruction that actually computes this address for us is called LEA. You could also pronounce it Leah, and it takes a source and a destination. And so the source is actually the address mode expression. So this like whole expression that we have here, something like this, any of these two things. So that would be your source. And then the destination is the where you want to put whatever you get, right? So whatever you get from memory by computing that address expression, you put that in the destination. And so let's take a look at a little example here. So let's say we have this function. It takes a value x and it just multiplies it by 12, right? And so if we want to do that in assembly, one way to do that is to also, yeah, so this function here also stands for load effective address, which is exactly what we're doing. We're loading the address, the effective address that's represented by the instruction. Yeah, so one way to do that is, so let's say we want to, so let's take the value in RDI, and let's say we want to multiply that by 3 first, and then we want to multiply it by 4. So, and that'll effectively multiply it by 12. So to multiply by 3, we can just take RDI, and so if we write it like this, this means that we're multiplying RDI by 2 and then adding RDI to it again, which means you're basically doing 3 times RDI. And oh yeah, so RDI contains X. And so you're taking X and multiplying it by 2 and adding X, which effectively just does 3 times X. And you're taking that value and putting that in the register RAX. And then this operation here, SALQ, basically shifts whatever you have left by in the destination by the source. So if the source is 2, then we're just left shifting RAX, yeah, so we're left shifting RAX by 2, and a left shift by 2. So a single left shift means multiplication by 2. So 2 left shifts mean multiplication by 4. So first we multiplied by 3, then we multiplied by 4, which effectively multiplies it by 12. And so this assembly code does exactly what this function does. And how to dereference twice per pointer. I guess you could just I guess if you want to do that, you could just kind of load, call Leah twice. And so the first time you would do something like this, and it'll turn out that at the memory address, there was another memory address contained instead of a value. And then you could call it again on that memory address, and that'll, how it's something like 11 times X work. Well, so it's not hard to find exactly how each C instruction would translate to assembly. It's up to the specific compiler, and I mean there could be a bunch of ways to do that. One way would just be to simply use the multiplication operand, right? So it could just do 11 times the value in your source. But this is just an example of how you could possibly do times 12. And this may be, so doing it this way may be faster for the CPU to handle it than just multiplying it by 11. So that might be a reason that the assembly compiler would generate it like this. But yeah, so if it's something that can't easily be translated into something like this, then I guess an instruction like this can be used, which would just be the multiplication instruction. Yeah, so these are the different arithmetic operations that were offered in assembly. And so we have add, subtract, multiply, and shift. And then we have the shifting ones. So shift arithmetic left, shift arithmetic right. And so this here is the logical version. So this is the arithmetic shift, and this is the logical shift. And you guys know the differences between those. And then we have the XOR, which is, yeah, that just XORs the destination with the source. And then we have the and the or. And the Q in these instructions just stands for quad in this case, and that signifies 64 bits. So the Q just signifies kind of the size of the parameters of the instruction. And yeah, and then something you need to definitely look out for is argument order, and make sure you input your arguments in the correct order, because the source and destination really matter. Yeah. So, and then we also have these other operations. We have increase, decrease, or increment and decrement, which just adds one, subtracts one. And then we also have the negation one, which just takes the negative. And also these only take one operands. Until now, we've seen instructions that take two operands, but this only takes one operand, and yeah, it just performs a single operation on it. And this last one not just negate, or I guess does the not of your whatever you pass in. A logical shift. So basically, a logical shift doesn't account for 2's complement, and just shifts the binary value over as many times as you want. But an arithmetic shift actually accounts for 2's complement, and when you shift it, if it's a negative number, it'll make sure to write it the 2's complement way. And then, so I just have an example here of a couple of these arithmetic operations that were offered. So first, what we do, so we want to translate this C code into assembly code. So to do that, okay, so we have these instructions that we're using. Basically, we're using Leah, which does the address computation. We're using SALQ to shift left arithmetic, and we're using the IMUL for multiplication. And this last one is only used once. And even the multiplication happens twice. And so let's see how this works. So let's say we have this assembly code label, a arith, and then which corresponds to this function. So what we're gonna do is we're gonna load. Okay, so first let's take a look at this. So RDI contains argument X, RSI contains argument Y, and RDX contains argument Z, which are the three arguments that the function takes. And then we'll see that RAX will actually contain multiple arguments, which will be overwritten, but they're only overwritten after that previous value is no longer used. And then RDX contains T4 and RCX contains T5. So so first we want to take our X and add it to Y. Sorry. So X is RDI, Y is RSI. So when we give it to the Leah instruction, it basically just adds these two together and puts that value in RAX. And RAX is what corresponds to T1 for us initially. And then we have the add operation, which basically takes a source and adds that source value to the destination, as you can see here. So we give it RDX, which is Z, and then we give it RAX as the destination, which is currently T1. So we do Z plus T1, and that's stored in RAX. And so we know that Z plus T1 corresponds to T2. So RAX now contains T2, as we can see. And we just overwrote the value of T1, but as you could see here, we'll never need T1 again. So it's totally fine to do that. And then we call Leah again. And this time what we want to do is this third step here, which does X plus 4. But we're not actually doing that yet, and you'll see why. So right now, all we do is, so we take Y, and we basically multiply it by 3, because we do 2 times Y plus Y, which is the same thing as doing 3 times Y, and we store that value in RDX. So T4, okay, so what we want to do is do Y times 48, right? But right now, we're just multiplying it by 3. And we store that value in RDX. So this step here isn't actually complete yet. And so we multiply by 3, and then we do this shift arithmetic left. So basically shifting it left by 2 or by 4 multiplies it by 2 to the 4, which is equal to 16. So we take Y, multiply it by 3, then we multiply it by 16, which effectively multiplies Y by a total of 48. And so that this step completes this T4 line here. And then we have another instruction for Leah where we have a displacement. So what we're doing here is, so in this case, we're doing T3 plus T4, right? And RDI contains, wait, what does RDI contain? Yeah, so RDI contains X, and RDX contains T4. So what we're doing is adding the value in T4, which is what we have here. And to that, we're adding X. And wait, 1 second. Then we add 4. How do we do that? So we want to do T3 plus T4, and T3 plus T4. So where did we? Okay, so we don't have the value for T3 stored in a register right now. So what we're doing is So RDX contains Z, right? And then RDI contains X. So this is kind of throwing me off. I went through this before and it made sense. Okay, yeah, so I'll come back to this later, but this is gonna store the value of T5 in RCX, and then we just use the multiplication operator to multiply T2 times T5. And so yeah, T5 is contained in RCX and RAX contains T2. And then we multiply the T5 times the T2 and store the value in RAX. And RAX is also the return value. So yeah, whenever we return from a function, it returns whatever is in RAX. And so when we return that, it returns whatever value we have in RAX, which is the R val that we want to return. And yeah, so that's basically how this this code translates into the assembly, right? Yeah, so just give me 1 second. What? Hmm. Okay, okay. I understand what they did here. Yeah, so basically, um, RDI contains X, and we're adding 4 to that. And X plus 4 is what T3 was. So in this step, um, oh, Eric, you got it? I mean, yeah, if you want, you could explain it. But yeah. So yeah, so RDI contains X, and we add 4 to that, and that's effectively what T3 was. And then we also add the value in RDX, which is T4 to that, which results in our value for T5. Okay, yeah, that makes sense. And then, okay, so I guess now we could go over BOM Lab and how that's gonna work. So, okay, so I mean, so did this make sense to everyone, or are there any questions? All right, yeah, if there aren't any questions, I guess we could move forward. And yeah, so next we'll talk about BOM Lab. And yeah, so our goal is to diffuse the bomb without any explosions, right? And each time your bomb explodes, it results in a loss of 0.5 points. And as you go through it, there will be multiple phases. So there are a total of 6 phases. And in each phase, you need to enter. So whenever each phase runs, it'll ask you for an input. And you need to enter the correct input in order to proceed to the next phase. So to find this input, you could look at the assembly code for hints. So there might be different hints hidden in comments in the assembly code or something. And basically you just need to go through this code, the assembly code for that phase, and figure out what it's trying to do. And basically based on that, you'll figure out what the input value is, and then you could enter that, and it'll proceed to the next phase. And so an explosion will occur when the explode bomb function is allowed to execute. And so that executes when you enter an incorrect input. And I'll show you guys how you can stop that function from executing and basically never lose points as you're working through this. Because last year, or yeah, so when I took the class, there were a lot of people who didn't set breakpoints in their BOM and allowed the explode BOM function to run many times. But you could actually go through the whole lab without your BOM exploding once if you use GDB correctly. And yeah, so I guess I'll just pull up an example BOM for you guys and show you how to use it in GDB. But these are the commands that we'll be using mainly, and this slide's going to be posted, so you guys could refer back to this. And I also linked a GDB cheat sheet here, and here a lot of the things that I'm talking about can be found, such as how to set breakpoints and executing and things like that. So just give me a second. I will share my terminal and log into iLab. Okay, you guys should be able to see my entire screen here now. And let me open my terminal. And then on the side here, I'll also have one second. Okay, so have you guys gone through this write-up yet, or is this your first time looking at it? Okay, well, it was only released like a couple days ago, so I'm assuming you might have not. Okay, yeah, it is pretty confusing. So hopefully I could clarify it. So it's based around this whole story of someone named Dr. Evil, and he built this, or she built this binary BOM lab. And yeah, so basically what you need to do is you go to this website here. To actually obtain your BOM, you need to enter your net ID and your email. And from there, you can download the BOM. And you need to take this BOM and transfer it, or the tar file that you get when you download it, and transfer it to iLab. And you can only do this on these 4 iLab machines. So make sure that when you're doing this project, you do it on iLab, or else it might actually explode the BOM if you try to do it on your own computer. And yeah, so from there, you need to run this command to untar the BOM, and you'll get a directory. And in that directory will be 3 files. A README, it'll just have your net ID, and the actual BOM, and you'll have the BOM.c file. And this BOM.c file, I mean, I'll show it to you guys and go through it. And then, yeah, so you just need to, each phase the first 4 phases are worth 10 points, and each phase, and the rest are worth 15, and it's a total of 70 points. And yeah, each time though your BOM explodes, it'll notify the server, and you'll lose half a point. And yeah, so you could actually go online and look at what your score is using this link provided here. And yeah, so I'll also go over what's happening here with the mysolution.txt. But okay, so I think the best way to explain it would just be to dive into the thing. So I'll SSH into iLab. And then I will cd CS211. Okay, and then yeah, and then I'll cd into PA4. Okay, so this is where I have it all set up. So here, I downloaded I downloaded this BOM, and I had it as a tar file. So I ran the command to untar it, and I got this BOM35 folder here. So now if I go into it, you could see that the three things are here: the actual BOM, the BOM.c, and the README. So if we take a look at the README, that just has your BOM number and your net ID and email. And then let's take a look at the actual BOM.c file here. So if I do, if I just print out the BOM.c file. So basically, this is the file, and it starts here with the main function. And so it, okay, so basically, let's just start from here. So it initializes the BOM, and then you can, what it does is it takes an input, and then it calls this function called phase1. You don't have access to these functions, this read line function or the phase1 function, but like you don't have the access to the C file that contains these, or else that would defeat the purpose. But yeah, then it calls phase1 using the input you gave it, and if your input is correct, it diffuses the phase. Otherwise, it explodes the BOM, which means you lose 0.5 points or half a point. So that's what it does for the rest of all these phases. And so let's just go. So now so that's basically what that C file looks like. And then to go into the BOM and actually diffuse it, you have these possible tools. So you have GDB, you have the object dump, and you have the strings command. So let's see what happens when we run this. So what that does is it gives me all of the symbols inside in this binary file, and this could be useful, but you don't have to use you don't have to look here. There's other ways of diffusing it, and then this is how you actually see how you actually see the assembly code associated with the BOM. So if I scroll to the top, it's pretty long. Yeah, so here we could see that we have phase one. This is the code associated with phase one. We have phase two, the code associated with that. And in each of these phases, there might be other function calls, and you could also see the code in those function calls. Phase three, and then you have like these functions that might be in some of these phases, and those are all here, right? And like this is used in the first phase, and you could look through this function to see what it's doing. And yeah, so that's what that gives you. And this just prints out all the printable strings in the BOM. So these are just all the strings that are associated with the BOM that you could access. And so the most important tool that you'll be using here is GDB, which I'll go into now. So to enter GDB with the BOM, I just do GDB BOM, right? So now I'm in it, and I can type run to run the BOM, and it'll ask me for the input to the first phase. But before I do that, because I don't know what the correct input is, right? Because I still need to diffuse it. What I'm gonna do is, so that the BOM doesn't explode from my wrong input, I'm gonna set, so in GDB we have breakpoints. So if it reaches a certain point, it'll just stop there. So if I set a breakpoint at explode BOM, the breakpoint will be set And when this function is called, when it reaches the stage of calling explode bomb, which actually explodes it and sends like everything to the server, it'll stop right before it explodes. So now if I type run, the program's waiting for me to enter the first answer. So, I mean, I don't know what it is, so I'm just gonna type hello or something, right? But when I typed hello, um, it was the wrong answer. So it encountered the first breakpoint, which is explode bomb. If I didn't set this breakpoint, it would have gone into explode bomb, executed it, and I would have lost half a point. So since the breakpoint was set, it's actually right at the location of where it's going to go into this function, but it has not entered it. So now what I'm going to do is I'm going to disassemble phase one to see what it's like, what's going on in there, and that'll be useful for me to uh, basically find what the correct string should be. So I'm going to use this function called it's the disassemble function, but you could this is a short form for it. So I'm just going to type disassemble phase one, and when I do this, it'll give me the assembly associated with phase one. And I can basically, well, I'm not going to go through it because you guys probably have a very similar phase one, but the bombs do vary. But yeah, so you guys have, I'm not going to go through it because that'll just give away the answer. But yeah, so what you want to do is go through this assembly code and see what's going on. And you can print different things. So you can print what's in a register or add some memory address. And printing these things could either reveal what the secret code is, or it can tell you what the function is doing. So you can figure out like the combination of numbers that unlocks it, or figure out the pattern of numbers that might unlock it. And yeah, that's fine. You're free to leave if you need to leave. But yeah. This is recording and it'll be posted, and then the slides will also be there if you need to refer back. So if you wanna print something at a register here, you can use this X command, and the /s will print whatever is at the register or memory address as a string. So I'll do X/s, and let's say I do that for I want to print whatever is in RSP, right? So to do that, I need to do $RSP, and then it'll print whatever is at that location. And this is what's at that location right now. But yeah, so basically that's how you can print things in different memory addresses. So here I could have passed the memory address too, and that would have also printed it. But that's how you could print stuff at registers and memory addresses. And another useful command you could use is the IR command. So basically what this will do is it will tell you what it will list all of the registers out that that this program accesses, and or just all of the registers that are available and exactly what value is in them at the time. So for this specific phase, you won't need to do this, but for future phases, you're gonna need to basically examine how values in registers are changing so you could figure out a certain pattern or something. And that'll allow you to find the solution to the phase. And yeah, so these are functions that'll help you a lot, especially the breakpoint. Do not forget to set breakpoints or else you'll be losing points. And here's a whole list of things you could do with GDB that could help you out. And yeah, so basically once I find the correct, once I go through this and I think I know the correct answer, I can quit out of this and run it again. And then actually what I want to do is I want to create a file called called mysolution.txt, or whatever you want to call it really. But this file will contain your solution, right? So let's say I found the solution to the first one, and I find out that the solution is world, right? Then I'm just gonna type that into the my solution, and next time I run it in GDB, I'll do run my solution.txt. So um, so let's say I do that, and then I call GDB again. I'll set a breakpoint because I still don't know if my answer is correct, and I'll do run my solution.txt, and then what it will do is it'll look at the first line in your text file, and that'll be the input to the first phase. And it was wrong, so it still went to explode bomb, but it didn't explode it. But when it's correct, it'll just go to the next phase and ask for that input. And if you have more lines in your mysolution.txt, it'll just keep reading through that and going through the phases and entering your input. So that way you don't have to memorize like what the input to phase 1 was when you're at phase 4. And then so everything's just in that file. Every time you find an answer, put it in there, and the BOM will take care of it itself, and then it'll just stop at the next phase, or at like the explode BOM point in the next phase that you have unsolved. Do we need to diffuse one BOM with no explodes to get the full? Yeah, so every time if you explode once or twice, you might as well give up and try on another BOM. Okay, so the thing is, well, I'm not completely sure if you could download multiple BOMs off the same ID, but or how that works. So I would recommend that you don't do that. But also, if you do that, the phases differ. So like, if you made progress through like 3 phases, and then you messed up on the 4th phase, you forgot to set breakpoints or something, then and then you lose points, you're gonna have to do the first 3 phases again for the different BOM. It's not gonna be the same answers most likely. So that'll just be more of a hassle for you, honestly. But yeah, so you need to just take one BOM and go through all the phases and diffuse it. And yeah, so that's basically how this works. And yeah, every time you solve a phase, it'll automatically be uploaded to the server that you did it, and your point value will update. And yeah, so that's all I had for today. And that's just my explanation of the BOM Lab and everything else. And I'll just end the recording now. And you guys could leave. Have a good day.